We're now going to take a look at some properties of the vector functions that relate to the derivative. And in some ways, it's kind of a hodgepodge of a few different types of properties. A couple of them have to do with extending the product rule that we know, like what does it look like? And then a couple of them has to do with some geometric properties of the curve itself and how those properties relate to the derivative. So in a sense, it's kind of the, when you think back to your first course in single variable calculus, where after learning how to compute the derivative, you kind of, you could say, well, it's used to analyze certain properties of curves. That's kind of what we're going to do now, but not to that degree that you'd have done previously, right? But so these are just a couple concepts that you need to keep in mind. And the first one is the notion of smoothness. So I am going to draw a pair of vector functions. So I'm going to draw their curves. And it doesn't matter if it's in R2 or R3. The concept is exactly the same. So let's say my first curve starts at that point. And notice how I've kind of traced it out in this direction. And then let's say it stops there, right? So on the curve itself, I can put a couple arrows to essentially show the direction that the curve itself was traced out. And that direction is pretty important, so the arrows, I'll just say these arrows indicate what we call the orientation or the direction of the curve. So indicate the orientation of the curve. Just a fancy way of saying how is it traced out as my parameter increases. So as t gets bigger and bigger, how does the curve get traced out? Well, essentially it does it this way, right? But then I can draw another one. I can draw another one that starts here, and then there, and then there, and then there, right? So in this case, that orientation is like this. And there are other names for it. You'll learn other names as we get deeper into applications of this stuff. You'll learn other names of it. So these are my two curves. There's one thing about this curve that kind of stands out, and it's the existence of these, what we might refer to as sharp corners. Right? Or nodes, if you will. Right? So you notice even when I was drawing out, it's almost like when to do that kind of abrupt turn or change of direction in the orientation, it's almost like I had to pause. Whereas I mean, instant, just for an instant, it's almost like I had to pause. Whereas over here, I did it smoothly. There was no pause. There was no kind of jerky, instantaneous start and stop in my motion. So it turns out it's the derivative, right? The derivative of the vector function, something about the derivative would cause these sharp corners and nodes. And again, that's not a foreign idea, because we saw that in Calc 1, right? So, what exactly is it? So we have a word to distinguish between this type of curve and this type of curve. This type of curve is described as being smooth for obvious reasons, and this type of curve is non-smooth for, again, obvious types of reasons, right? Now, when we're talking about smoothness of a curve, we're not going to really apply the definition to the endpoints of the interval, if there are endpoints. because it could be a situation where the vector function is defined for all values of t. So you could essentially have this infinite curve. In that case, again, there will be no endpoints to even worry about. But in the presence of endpoints, the definition that I'm going to write down, and the definition will make light of that. Well, not light of that. It will make that clear that if it's a finite curve, we ignore what happens at the endpoints because we don't know. We don't know if the smooth pattern continues or it ends up being a jerky, non-smooth pattern, right? So I just said jerky. How did that get into a calculus discussion? Anyway, so let R of t be a curve in R2 or R3. Technically, it could be Rn. Let's say defined for. So what I will do is I will do this. I'll write this interval with the understanding that both a and b could be, so a could be negative infinity, b could be positive infinity, and then I would drop the equal signs, right? So it could be an infinite interval, either one-sided or doubly infinite. But let's say we have a vector curve that's defined for all values of t between and including a and b. R of t is said to be smooth on the open interval, so that's where we take out the endpoints, if this is true, right? So for smoothness, the first thing we require is that the derivative function must be continuous, right? So r prime of t is continuous. So is continuous for all t in this interval. Again, allowing for a and b to be plus or minus, minus plus infinity respectively. And something else has to happen to avoid those sharp corners. And what has to happen is this. The derivative function is never equal to the zero vector for all t in this interval, right? So for all t in this interval. So if we make sure that our derivative vector is never always equal to zero, then our curve is always going to be nice and smooth, right? So let's take a look at something. So let's look at an example of this. So in fact, let me use f and g. I know we've been using r a lot, but I just want to show that, yeah, we can use a regular f as long as we, again, indicate that this is a vector. So let f of t be this function. And g of t be this function, t minus 1 squared, and then say t minus 1 cubed, and let's say 2, right? So these are these two functions. So the question is this, is f of t, is, not if. So is f of t and g of t smooth for all real values of t? So in other words, if we were to use software, right, and generate these curves for any range of values of t, our set of values of t, would we see a nice smooth curve, or would we see something that has at least one sharp corner somewhere? Well, in order to answer this question, we have to see if both of these two properties are satisfied. So let's apply these two conditions to f and see if f passes both of these. So it says, so obviously both of these involve the first derivative. So let's find f prime of t, our derivative of this vector function. So we have 4e to the 4t cosine of t and 2t. All right. So if we look at this, look at the components of this vector function. 4e to the 4t cosine of t 2t. These three functions are always continuous, right? So I'll say 4e to the 4t cosine of t and 2t. These functions are continuous for all real numbers, right? So these are continuous for all real numbers. My thing is a little jerky today, so it's continuous for all real values of t. So it passes the first check, right? So the derivative has to be continuous, and that's good. The next question, the way you or requirement, the way you interpret this as saying is that there is no value of t that when you evaluate the derivative, right, you would get the zero vector. So essentially, let me kind of highlight what we're doing, checking each property. But let's say you go to check the second property. What it's asking you, if you were to set each component equal to zero, because that's how you would form the zero vector. Each component would have to be equal to zero, right? If you had a single value of t that would satisfy all three equations, right, then we would say that the vector function is not smooth at that value of t. Okay, so let's start with the easier of these three equations to solve. So this tells me that, oh, the third component is going to be 0 whenever t is equal to 0. All right, so we have that. This is our cosine function. The cosine function is going to be 0 at every odd integer multiple of pi over 2. So this implies that t is equal to n times pi over 2, where n is an odd integer. All right, so you have to remember this trig equation, it has lots of solutions, so pi over 2, negative pi over 2, 3 pi over 2, negative 3 pi over 2, etc. So in fact, let me just kind of write it out so you can get a sense. But this is an infinite set, so we obviously can't list them all. So I'll just say negative 3 pi over 2, negative pi over 2, and then pi over 2 going this way, 3 pi over 2, etc. So the next one will be 5 pi over 2 in this direction, and then negative 5 pi over 2 in this direction, right? So first of all, we see that even though both of these two components could be equal to 0, it's not the same value of t that will make them equal to 0, right? Because if I plug any of these values of t into 2t, I am not going to get 0. And similarly, if I plug 0 into my cosine function, it's not going to be 0. The cosine of 0 is 1, right? So the set of solutions for this equation does not intersect the set of solutions for this equation. But then look at the first equation. This tells us even more. In fact, we could have started with this and realize that your exponential function can never be equal to 0. So this has no solution, real or otherwise, right? So there's no way the first component could be equal to 0. Hence, this vector function, it's smooth for all values of t, right? So again, what all of this implies is that my derivative function is never equal to the 0 vector for all real values of t. So then the conclusion is, so therefore, my vector function, the original function, is smooth, right? So again, what we're doing here, we're using properties of the derivative function to make a kind of a geometric characterization or classification of the original vector function. So because the derivative is a nice, it's always continuous, right? And it's never equal to the 0 vector, then f of t is smooth, right? What about the other one? So let me write down my g. So g, if you remember that vector, we had t minus 1 squared, and then t minus 1 cubed, and then I think I had 2 as the third component. So the third component here is a constant. Well, let's go ahead and differentiate it. So I'm going to start by checking property 1. So the derivative of this vector function, not very difficult at all, but we just have to remember to use our chain rule. So it's 2 times the quantity t minus 1, and then 3 times the quantity t minus 1 squared, and then 0, right? So we look at this and look at the components of each of these. Constant functions are always continuous. Polynomial functions are always continuous. So the derivative vector, again, is continuous for all real numbers. So that's good, right? But what about the second property now? What if we take each of these components, set it equal to 0, and see if it's possible, right? And if it's possible for the same value of t, that's where we're going to run into our sharp corners. So set that equal to 0. Set that one equal to 0. Now the third component is always 0. So this is already satisfied, right? This is what we call a tautology, something that's always true. Well, this is not always true. The first equation here is only true when t is equal to 1. Same thing. The second equation is only true when t is equal to 1. Uh-oh. So there we run into a problem. So at t equals 1, my g vector function would not be smooth, right? Because so what this is saying is if you were to take my derivative vector and evaluate it at 1, look at what you would get. You'd get 0, 0, 0. So you'd get the 0 vector. So at this point, or I should say, so this is our 0 vector. So therefore, it's smooth for all other values of t, but not at t equals 1. So g of t is not smooth at t equals 1. So if we were to graph the curve, this function here, right? And look at t equals 1, we would see a sharp corner, right? So it's a little bit different than how we identified, points of non-differentiability in calculus. Well, then we weren't using vectors in Calc 1, right? But now we're showing that using vectors, it's the idea of where your derivative vector, essentially what we say is, does your derivative vector ever vanish? Because the vector will vanish if it has no direction and no magnitude. And this derivative vector vanishes when t is equal to 1, therefore not smooth. All right? Okay, so that's the idea of smoothness. The other thing I wanted to mention is just, I want to revisit the product rule, right? So, or in fact, what I'm going to say is product rules. So we know if we have two, like, again, let's say scalar functions, like just a function of x, and we multiply them, if they're both differentiable, well, we have a rule for computing their product. Well, when we move to vectors, we essentially have, I mean, if we really are nitpicky, we essentially have four ways that we can multiply vectors, right? Um, Vector functions, that is. So what I'm going to say is, let's say this. So I'm going to define a couple things. So f of t and g of t, let's say these are differentiable. In other words, their derivative exists, right? So these are differentiable functions in R2 or R3. Again, everything's going to work for either the plane or space, right? So these are differentiable. Then suppose I have, I'll call this like just a k of t. This is a scalar function. So this one is not a vector. It's like, like t squared, or the square root of t plus 1. That's this. So this is a scalar function. So it's a function, but it produces a number as opposed to these functions that produce vectors. And then suppose we have c is a real scalar, right? So the reason I'm saying that there are four kind of products we could do. So for instance, one thing we can do, and this is one of our basic vector operations, is that we can take a constant and multiply a vector. So I could take c, for instance, and multiply that vector function. And that is one version of a product. So this is like your scalar multiplication. And the question is, well, what happens now if I take the derivative of that, right? So what if I have to take the derivative of a constant times a vector? Well, it turns out that constant multiple rule, right, from your first semester of calculus or first course in calculus, it holds here as well, because I can take the constant out and then just multiply the derivative of my vector function, right? So this is like this is your constant multiple rule, right? So let me write here. So this is the constant, or I guess you could say scalar multiple rule if you want. So constant, I'll go ahead and say constant multiple just to be consistent with what we said previously. All right, so that's one type of product. The other type of product is where you could take a scalar function and multiply one of our vector functions. So you could have this. So you could take the k of t and multiply, let's say again, just f of t. I'm not picking on f. We could do it with g, but basically for these, I only need one of the two functions, vector functions, that is. Now here, this is no longer a scalar, but it turns out our product rule works, right? But this is not on here. I know I'm using a dot, but this is not a dot product because these are not two vectors. This is a scalar, and we're just multiplying this vector function. In fact, we would do it the same way as we would do our scalar multiplication, simply by using the distributive property. So I will just say that, note that this is scalar multiplication, right? So scalar multiplication, right? And with that, we can use our regular product rule. So again, the product rule would say take the derivative of the first times the second, and then plus the first times the derivative of the second. So I'll use my prime notation there, right? There we go. So this is your basic product rule, right? So this is your basic product rule. And it would have to be applied here because now you're multiplying the vector function not by a scalar constant, but a scalar function. Well, let's think about vector functions now. What type of products do we know that we could perform with two vectors? Well, we could do a true dot product, right? Or we could do a cross product. And it turns out that the product rule, this version here, still holds even if I am doing dot products there or cross products there. So that's really helpful. So again, I'm not going to formally prove these. I just want it's something to be aware of, because when you now talk about multiplying vectors, the question is, well, what type of multiplication are you doing? So if you're now doing a vector f dot, so I'll make this one a little bit bigger, with a vector g, right? So it's not scalar products anymore, but now a dot product. It turns out that this pattern still holds. So what you would do is you would take, again, the derivative of the first function and then do a dot product with the second function, again, all vectors here, and then plus the first function, and again, dot product with the derivative of the second, right? Notice now all the factors here are vectors. That was not the case in the previous rules. This is not a vector, it's a scalar constant. This is not a vector, it's a scalar function. These are now all vectors. So that's why, again, to multiply them, we would have to use one of our, ways of multiplying vectors. So this doesn't, I'm going to coin my own little phrase here and say this is like my dot product rule, right? So don't quote me on that, but I think it's just a way of distinguishing, the operations. And then finally, I can replace the dot with the cross and it still holds. So that's nice. So if I have to do, now when I'm doing the cross product, remember the cross product requires a vector with three components, right? So we would assume that both f and g, they have three components. So if we're taking the derivative of a cross product, then it would look like this. Again, I always do the derivative of the first, and then it would be crossed with the second, and then plus the first, and then crossed with the derivative of the second. So you can think of this as your cross product rule for derivatives, right? Now, in practice, particularly with the dot and cross ones, it's often easier to do the dot product first, right? Because you can always do the dot product of vectors in either R2 or R3. And you can always do the cross product here, and then the result, you would do your differentiation. But it's nice in certain like proofs or certain more theoretical questions to be able to expand this derivative as to get an expression like this. So in other words, it's sometimes useful to be able to write it out symbolically to determine other results or to see other patterns. All right? Okay, so I just wanted to state those. The next one that, again, is kind of related to the derivative, and in fact, we are going to end up using this particular result. It's a theorem that is actually very, very useful, and it has a nice geometric interpretation to it. So this is a theorem, and it basically says this. if the magnitude of your vector function, whether it's in R2 or R3, so if the magnitude of your vector function is equal to a constant, right? So, or k is some constant. So in other words, the magnitude never changes, right? If the magnitude of the vector function is always a constant, and R is differentiable, right? Then it turns out that the vector function and its derivative is always orthogonal to each other. So then R and R prime are always orthogonal. In other words, the original vector function and its derivative, right, are always going to be at 90 degrees, regardless of what t is. And here is so what I'll do is I'll give you the proof, and again, later on, we'll kind of explore what that means, like visually. Now, going back to what we did with the dot product, recall, that doesn't look like so recall that when you take the dot product of a vector with itself, you might remember that we get the magnitude squared, right? So when you take the dot product of a vector with itself, you get the magnitude squared. But in this case, we're assuming that the magnitude is a constant. So then this would be my constant squared. All right. Well, let's differentiate both sides here. So let's differentiate. So let's take the derivative of the left-hand side. So the derivative of my dot, in fact, this is a dot product. Let me make it that big and clear that here we have a dot product. And then we would have to take the derivative of the constant. So let's do the derivative of that. All right. Now this is where we need the product rule, right? Because we don't have an actual formula, right? We don't have actual components for R. We just know that it's a vector function. We know that it's differentiable. So everything here makes sense, right? So we're going to use our product rule for for our dot. In fact, let me say this. We're going to use our dot product rule, and we're going to end up getting derivative of the first dot with the second. So like that, which is just and then plus the first dotted with the, again, big dot there for dot product with the derivative of the second, right? So we have that. Now, when I differentiate a constant, I know that is going to be 0, right? So that's equal to 0 because a k squared is a constant. Now, another property from the dot product, remember that the dot product is commutative. So whether I take r prime dot r or r dot r prime, I'm going to get the same result. So these two expressions are the same. So I have one thing added to itself, so then I'll have two of that thing. So I'll have two, I'll write it like this, r of t dot r prime of t, and then that's equal to 0. So I can divide both sides by this constant. So what this implies is that the dot product of the original function and its derivative function is always equal to 0. And remember, whenever the dot product of two vectors is equal to 0, it means the two vectors are orthogonal, right? So regardless of what t is, so therefore r and r prime are orthogonal vectors, right? And that's our QED, right? And again, it might seem like kind of an odd result. Why are we looking at something like this? But believe me, it will come up in future work. Like, what happens if we happen to know that the magnitude of a vector function is equal to a constant, then we know an immediate and important relationship between the vector function and its derivative. And the way you can visualize it is really interesting, and I guarantee you we will see it visualized in the future. But here we're just kind of again establishing more properties, and all these properties are based on the derivative. So hopefully you've enjoyed seeing how the concept of the derivative of certain products can be extended, and the concept of smoothness is defined in terms of derivatives. And here, this nice relationship between a vector function and its derivative, provided that vector function has a constant magnitude. All right, see you in the next video for more calculus of these vector functions.